All right, everybody, get ready. Because today we are taking a deep dive into making those crazy realistic computer graphics.
You know, the kind that make you wonder if it's a video game or actually real life.
Yeah, exactly. Have you ever wondered how they make those graphics look so lifelike?
Well, it starts with a little something called a BRDF.
Oh, here we go, BRDF.
It sounds complicated, but it's actually a pretty simple idea.
Okay, I'm listening. Break it down.
Imagine like shining a flashlight on a bunch of different surfaces.
Okay, got it.
The way the light bounces off like velvet, it's completely different from how it reflects off a mirror
Hmm.
or even a brick wall, right?
Yeah, totally different.
BRDFs are how we capture those unique interactions digitally.
So BRDF is basically the science behind making virtual surfaces look real. And today we're specifically talking about microfacet BRDFs, right?
Yes. Those are the workhorses behind so many of the incredible visuals you see in, games and movies these days.
And they're super interesting because of how they break down complexity.
Right. Like, imagine if you could zoom way in on a surface,
Okay.
like with a microscope, but like a super powered one. You'd see all these tiny little mirrors. They're randomly oriented, and those are called microfacets.
And we can simulate how light interacts with all of them to get those realistic surfaces.
Exactly. Instead of trying to model the whole surface all at once, you break it down into these tiny little pieces.
That's so clever. But I'm seeing in our sources here that microfacet models, they're still models.
Of course.
So they still involve some simplification, right?
Right. Absolutely.
Yeah.
Like any scientific model, we have to make some assumptions to simplify the problem a little bit.
Otherwise, it gets too complicated, right?
Yeah, it's like assuming that the Earth is perfectly round when you're, drawing a map.
Right.
It's not perfectly accurate, but it's good enough for most cases.
Yeah.
And in microfacet models, one simplification is that a lot of times we're focusing on those geometric interactions of the light,
Okay.
when in reality, the physics of it are even more complicated.
Yeah. I mean, there's a quote here that says, calling them physically based doesn't mean that they're perfectly predicting how light's going to interact with a real surface.
Right.
It's more about finding a good balance.
Exactly. It's about making something that's useful and looks good, even if it doesn't capture every little tiny detail perfectly.
Totally. So that brings us to the key ingredients of a microfacet model, right?
Yes.
The components of our recipe for making realism.
Exactly.
And our sources are mentioning things like normal distribution function,
Okay.
geometric attenuation, which sounds exactly like what it is, and Fresnel reflectance.
Yes,
Those all sound pretty technical.
they do.
Can we break those down a bit?
Sure.
What are those things?
Think about it this way. If you want to build a realistic surface,
Mm-hmm.
we need to describe how all those tiny little microfacets are arranged,
Okay.
how they might be shadowed by each other,
Right.
and then how the light reflects off of them at all these different angles.
Okay.
So that's where all these terms come in.
Okay, so let's start with normal distribution function, or NDF. So that sounds like it's describing how those microfacets are scattered across the surface.
Exactly. You can think of it like a probability map. Like it describes the orientation of all those little microfacets.
Okay.
Different NDFs will give you different looks.
Oh,
It's like, imagine the difference between a brushed metal surface and a piece of velvet.
right.
The way those microfacets are arranged is really different.
Yeah, that makes sense.
And that contributes to how they look.
Okay, so it's like choosing the right brushstroke for your digital painting.
Exactly.
Okay, that's a great analogy. Then we have geometric attenuation
Yes.
or shadowing function.
Right.
That one sounds a lot like what it is.
It does.
Some of these microfacets are going to block light from hitting other ones.
Exactly. The shadowing function accounts for the fact that not every single microfacet is going to be lit the same way.
Right,
Some might be completely hidden, some might be partially shadowed.
right.
So the Smith model, it's a popular way to calculate that. And some models even consider the height of those microfacets
Oh, wow.
for even more realism.
So it's not just about the angle, but about how high or low they are, too.
Exactly.
Okay. And finally, we have Fresnel reflectance.
Yes.
And that one always makes me think of those cool reflections you get off, like a wet road after it rains.
Exactly. Fresnel basically describes how the reflectivity of a surface changes depending on what angle you're looking at it from.
Right.
So if you're way out at a grazing angle, you see more reflection.
Okay.
And if you're looking at it head on, you see less.
Right.
It's what makes puddles look super shiny when you're kind of driving past them.
Right. Right. Okay, so we've got our microfacets all arranged according to the NDF.
Right.
And some of them are casting shadows based on the G function.
Yes.
And then the Fresnel effect is making sure that those reflections look right from all different angles.
Exactly.
So these three things work together like a recipe
They do.
to figure out how light's going to bounce off a surface.
They do.
It's incredible how much detail goes into making these things look real.
And this is where it gets even more interesting, actually. Because just like you can tweak the ingredients in a recipe,
Okay.
we have choices to make when we're putting these pieces together.
Gotcha.
And those choices determine how realistic our rendering is going to be, but also how much power it's going to take to actually make those graphics.
So it's a balancing act between pushing for ultimate realism and making sure that the games run well.
Exactly.
Yeah, that's exactly it. Okay, so one of the debates that we see popping up in our sources here is about choosing the right shadowing model.
Okay.
And specifically, that's the Smith model versus something called V-cavity.
Right.
So let's dig into that debate. Like, why would a developer choose one versus the other? Okay, so last time we were diving into this debate about choosing the right shadowing model.
Right. We were talking about Smith versus V-cavity.
Yeah, what are the trade-offs there? When would you reach for one over the other?
Well, you can think of the Smith model, especially when you're factoring in the height of the microfacets. It's kind of like that artist who's really meticulous.
Yeah.
They want to get every single detail just right.
Right.
It's known for its accuracy. Especially when you're trying to render those subtle, those highlights you see on a rough surface.
Okay.
Imagine brush metal, and it has those long highlights. But all that detail, it comes at a cost. So computationally, it can be pretty expensive.
Yeah, so it's like rendering a super high-resolution photo. It's going to look amazing, but it might make your computer slow to a crawl.
Yeah, exactly. Now, V-cavity, on the other hand, it's more like a clever impressionist, maybe. It simplifies things a little bit. It's finding clever ways to kind of represent those shadows and highlights without needing as much horsepower.
Okay.
It may not be quite as precise as Smith, but it can still look really good.
Right.
Especially for real-time applications like games.
Right, so it's all about finding that balance. How good does it look versus how well does it run?
Exactly. And looking at our notes, it looks like the Frostbite engine went all in on realism.
They did.
Yeah, they opted for that height-correlated Smith model.
Wow, and it really shows. When I see those games and the lighting is so good and those highlights are just shifting across the surfaces.
It's really impressive what they've been able to achieve.
It is. But, we haven't even talked about indirect lighting yet.
Right.
It's one thing to simulate a light hitting a surface, but what about the light that bounces around a scene?
That's right.
How do you make it feel like the light from a window is actually filling the room?
Yeah, and that's where light probes come into play.
Okay, so they're capturing a snapshot of the lighting in a specific spot.
Exactly.
Yeah.
Imagine placing invisible cameras all throughout your scene, and each one is getting this panoramic view of all the light around it.
Okay.
So they record how much light is coming from every direction, and that lets us recreate that indirect lighting effect.
So that's giving the scene atmosphere, that subtle glow that makes it feel more real.
Exactly.
I'm seeing some different types of light probes in our sources, though.
Oh, right.
Like distant and local probes.
Yes.
What's the difference there?
You can think of it like the difference between, say, the sun and then a desk lamp.
Okay.
So the distant probes, they're capturing that big ambient light.
Right.
If you took a snapshot of the sky,
Okay.
it's that nice, soft, diffused light that's coming from everywhere. Local light probes, on the other hand, they're more focused.
Okay.
Imagine you're trying to capture the light that's coming from a lamp or reflecting off a nearby wall.
Oh, okay.
Something like that.
So distant is big picture, local is the finer details.
Exactly.
And it sounds like Frostbite uses both.
They do.
Yeah.
And they use those local light probes to add a lot of realism, especially to those indoor environments.
That makes sense. But how are they capturing all this information? Do they have little cameras running around in the game?
Well, not quite. It's actually done through simulation. They're basically using the game engine to look at the scene from the light probe's point of view.
Okay.
They're taking into account all those light sources, the geometry, and for those distant probes, they'll often use what's called a physically based sky model.
Physically based sky model.
Okay, now you have my attention. What is that?
Yeah, it's basically a way to simulate realistic skylight based on things like the time of day
Oh, wow.
or the weather or where the sun is in the sky.
So you can have dynamic lighting
Yes.
that changes throughout the game.
Exactly. just like in real life.
That's incredible. It's like those cool time-lapse videos, like where the clouds are moving across the sky.
Right.
But now it's happening in a video game.
I'm seeing a note here, though, like a warning about using like real-world HDR images for distant light probes.
Oh, right.
Why is that?
Well, the thing about HDR images is that, especially those ones that are captured with a real camera, they often go through a bunch of processing.
Okay. Yeah.
It's like adding filters
Yeah.
to your photos.
Right.
And all that processing, it can kind of mess with the light values.
Right.
And so they're not really accurate representations of what the real-world lighting would be like in your game.
So it's like trying to bake a cake using a recipe that was written in a different language.
That's a great analogy.
It might look kind of like a cake, but it's not going to taste quite right.
Exactly.
Okay, so we've captured all this amazing nuanced lighting with our light probes.
Right.
But now what?
So now we have to actually use it, right?
Yeah, right.
We have to figure out how to light our surfaces using all that data. And that's where we come back to our trusty BRDF.
Okay, so we prepped our ingredients. Now it's time to actually cook.
Exactly. But we want to combine all that lighting from the probes with how our surfaces actually reflect light, all while still making sure our game runs smoothly.
Right. Make it look good, but run well. It's always the balance, right?
It's always. And that's where this really clever technique comes in.
Okay.
It's called pre-integration.
Pre-integration. Yeah, I think we touched on that a bit earlier, didn't we?
We did.
I'm sensing a theme here.
Yeah, and it's just like preheating your oven.
Wow.
It can save you a ton of time when you're cooking. And pre-integration basically lets us bake in some of those complex lighting calculations ahead of time.
Oh.
So we don't have to do them in real time for every single pixel on the screen.
So we've gone to all this trouble to like capture this super realistic lighting.
Right. With our light probes.
Yeah, and pre-integrated everything to keep the game running fast.
Exactly.
But then there's that one thing that can still mess it all up.
Oh, yeah. You're talking about aliasing.
Aliasing, yeah. Those like jagged edges, they just ruin the illusion.
They really do.
Is there any way to actually get rid of them completely?
Well, maybe not completely.
Okay.
But we've got some pretty good ways to fight back.
Okay, that's good to hear.
But to, like, really understand how we solve it helps to understand why it happens in the first place.
Right.
So at the end of the day, we're trying to cram an infinitely detailed world onto your screen, which only has so many pixels.
Right. It's like fitting the entire universe into a suitcase. Something's got to give.
Yeah, exactly.
Yeah.
And with these microfacet models, where we're already dealing with these tiny little details, all those little bumps and grooves, it makes the problem even worse.
Right. It's like those old school pixel art games where you could like count the pixels.
Exactly.
We've come a long way since then, but it seems like those pixel limitations can still sneak in.
They can.
Yeah.
So what's our first line of defense then?
Well, one common approach is called super sampling.
Super sampling.
Yeah, it's basically like taking a really, really high-resolution photo
Okay.
and then shrinking it down to fit your screen.
Okay.
So by rendering the scene with way more detail than you actually see,
Right.
it helps smooth out those jagged edges. So more pixels means a smoother image.
Pretty much.
But there's got to be a trade-off there.
Oh, there is.
More pixels, more work for the computer to do, right?
Exactly. Super sampling can really slow things down.
Oh.
Especially if you're, like, cranking up the resolution really high.
So you got to be smart about it.
Yeah. And that's why people are always trying to find smarter, more efficient ways to do it.
Right.
Like, maybe we don't need to use all those extra pixels everywhere.
Just where they're needed most.
Exactly.
Yeah.
Exactly. And that's where, like, multi-sample anti-aliasing comes in, or MSAA for short.
MSAA, okay.
Yeah. So instead of super sampling the whole scene, it's focusing on the edges of things where those jaggies are going to be most noticeable.
That's really smart.
Yeah, it's a lot more efficient.
Okay. I'm also seeing some more, I don't know, exotic sounding techniques in the sources too, like pre-filtering and something called lean mapping.
Oh, yeah. Those are cool.
What are those all about?
So those techniques are all about, like, outsmarting the aliasing problem.
Oh, right.
Instead of just trying to brute force our way through it with more pixels,
Right.
they're trying to be more clever about it.
Okay.
Like, how can we capture the essence of those details without needing to render every little thing perfectly?
Okay, so less brute force, more finesse.
That's a great way to put it.
Can you give me an example? Like, how would that actually work?
Sure. Imagine, like, a piece of wood.
Okay, yeah.
Yeah, it's rough, right?
It is.
So these pre-filtering techniques, like lean mapping, they'd analyze the roughness of that wood and then bake that information into how the surface reflects light.
Wow.
So instead of
Yeah.
trying to render every single bump and groove,
Right, which would probably look terrible.
yeah, and be really slow,
Right.
we're kind of representing that overall roughness in a way that's just like smoother.
That makes a lot of sense. It's like instead of drawing the texture with all those tiny little details,
Right.
you're just capturing the overall feel of it.
Exactly. And the really cool thing is,
Yeah.
in some modern game engines, they can do this pre-filtering on the fly.
Oh, wow.
Yeah. So the engine can adjust the level of detail based on how far away you are from the object.
Oh, that's so smart.
So like if you're right up close, you see all that detail,
Right.
but then as you move further away,
Yeah.
it smooths things out to avoid those jaggies.
It's like the ultimate optimization.
It is. It's this constant balancing act between making it look good
Mm-hmm.
and making it run well.
Finding that sweet spot.
Exactly. And the crazy thing is, they're constantly coming up with new ways to do it, too. New anti-aliasing techniques are always being developed.
It's like an arms race.
It really is.
Mm-hmm.
But the main takeaway, I think, is from those tiny little microfacets
Yeah.
all the way up to how we actually draw the pixels on your screen.
Yeah.
Every part of that process is designed to make things look as realistic as possible.
Yeah. When I think about all the work that goes into it,
It's a lot.
it makes you appreciate those amazing graphics even more.
It does. It does. And, like, the best part is
Yeah.
we're still just scratching the surface of what's possible. Like, who knows what those graphics are going to look like in 10 years?
I can't even imagine.
It's really exciting.
It is. Well, folks, there you have it. We journeyed deep into the world of microfacet BRDFs, and along the way, we learned how to make insanely realistic computer graphics.
From understanding how light bounces off surfaces at a microscopic level, to those sneaky tricks for tricking your eye into seeing a smooth image.
It's been an amazing journey.
It has.
Thanks for joining us for this deep dive.
Until next time.
Keep those pixels sharp.